Hey everybody, this is Larry. This is me going over um, the, the 7th day of July for the daily Leetcode challenge. Cave smallest element in sorted a matrix. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Usually I solve these live and you could still see me solve this live afterwards, but because the video is long, I do an explanation in the beginning. So you could skip ahead if you like, because I do an explanation near the end as well. But to be honest, this one was actually really easy, pretty standard and trivial. The reason why it took so long was because I was trying to figure out a linear time solution, and then after half an hour I gave up, and then apparently there wasn't a linear time solution, so I just wasted half an hour for no reason. But let's go over this problem, and yeah, hope you all are having a good day. But basically there are couple of solutions. The way that I did it is with heap and heap sort. Yeah, but you can do it with regular sorting, just dump everything in an array and sort, or you can do some binary search logic, which I also go over a little bit. But there are a couple of ways to do it, but none of them is linear time. And when I say linear, I mean linear in the size of the input. And the size of the input is R times C, or maybe you'll see it as n squared in this case. Oh, is it always a square matrix? Oh, it is a square matrix. Then okay. Then maybe I actually misread that as well. But in this case, linear time is going to be n squared because that's the size of the matrix. Because that's the input size, right? And yeah. But I spent too long looking at for that solution and it didn't exist. So whoopsie daisies. But yeah, I'm going to go over the heaps solution. Definitely you could do it the other ways. I don't think they're all not that interesting, to be honest. But maybe the binary search one could be interesting if you could kind of do a row by row elimination type thing and then search. But in any case, but yeah, so what I have here is I just set up the rows and columns, and this works more generically and not assumes that it's n by n. But either way, we basically create a frontier of sorts of just basically starting with the corner with the smallest number, and then we kind of slowly expanding out, almost like a Dijkstra algorithm type thing, where you're just kind of trying to find the cave smallest number. And that's basically what we have here. For every time we pop, we subtract 1 to see if it's the number that we need to return. If it's not, then we either go down or to the right, and then we check that it's still within the bounds and that we haven't already done it. And if we haven't done it, then we set it to true, and then we add it to the heap to be popped later in the future. Because for each element each element may be pushed and popped once, so that's going to be a very natural n squared log n. If you want to say n squared times log n squared, but then log n squared is equal to 2 times log n, so that's why it's equal to O of n squared log n. And of course, space is just going to be, for me anyway, n squared, because we keep track of this done flag. Cool. That's really all I have for this one. Let me know what you think. But stay tuned. You can actually watch me solve live and explain my thought process around a linear time solution, which I didn't get, obviously. Next, it's a little bit disoriented because you'll see my original intro as well, but hope that's okay. Anyway, that's all I have. I'll see you later. See you tomorrow, and see you in a second. Hey everybody, this is Larry. This is the 7th day of the July Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think. Happy Wednesday, hump day, all that stuff. I hope y'all are having a great week. Let's get today's problem started. Cave smallest element in a sorted array, matrix. Okay, yeah. So I usually solve these live, so it's a little slow or suboptimal, fast forward, or whatever you need to do. Okay, so it is sorted in ascending order. Okay. So each of the rows, and this is a very awkward way of putting it. I think I've seen similar problems before, but it's basically that, for example, here, yeah, like, okay. Yeah, they're sorted rows independently and, or columns independently and rows independently, right? So yeah. Yeah, most 300 by 300 order, okay. Non-decreasing order is a little bit hard though. Because the thing is that if the elements are distinct, then you can make assumptions. But if they're all the same, then I think the worst case, like for example, if all the numbers are all in the entire matrix is the same, then you really cannot do it in a faster way. Like because you have to make some decisions in a weird way, right? So these are always feels a little brain teaser-y as well, but let's play around with some numbers and kind of see if I can figure out the pattern here. So basically you have this matrix, for example, and okay, so if we sort it, it'll be 1, 5, 9, 10, 11, 12, 13, 14, 15, right? So basically you have this my idea here in some way is always going to be trying to figure out how the frontier is, and frontier is just basically like almost like things that are at the boundary, if you want to call it that, and figure out how to move that frontier or move something in that search of the frontier in a good way that is better than linear. And I think obviously, just to be clear, we can definitely sort. We could put all the arrays in an array, all the elements in an array, sort it, and get the answer pretty quickly. And it would actually, to be honest, be fast enough, right? Because it's 300 squared. 300 squared is what, 90,000. 90,000 log 90,000 is way fast enough. But just to be clear, I'm just trying to figure out if there's something that's more linear, because n log n is trivial, and I don't know if it's worth doing because that just, like that is way basic otherwise. So okay, so let's see if there's any invariants that we can think about as we move. Okay, so with these problems, there are only really a couple of ways to move. Like if you try to be exhaustive in like, we don't have any idea what I would do, and I don't have an idea right now. So what I'm doing is just trying to think about, okay, we're trying to think a linear time algorithm. We can only visit each node once, right? Or constant number of times, say. And in that case, that means that let's say if we start on any cell, we have to go monotonically decrease the size of the search space, and there are only four places that maybe 5 if you want to count the middle, say, but I don't know if that makes sense, but I'm just saying, like, in theory, right? And it means that you start with either one of the corners and then move somehow, start with the total number of elements, and it's in a way try to figure out the process of elimination to figure out how to find the numbers in between, right? So let's play around with that idea. I think maybe this corner or maybe this corner will give us the most information, because this corner will tell us how many, and by symmetry, these two are roughly the same, because you can always just flip it you can always flip it that way, right? And the idea here is, okay, let's say I have 12. What does this mean, right? That means that I have at least row minus 1 column of numbers that are smaller than it, and columns minus 1 numbers that are bigger than it, right? Meaning that all the numbers to the right, we know that it's going to be bigger, and all the numbers to the north or up, it's going to be smaller. So what does that mean, right? That means that if we go up, okay, so I think that seems to be a reasonable answer, right? Because that means that, okay, if we go up, we eliminate k, sorry, not k, but you remove a number of items, right? And then you go up, and if it is in this row, then you can just figure out by going to the right. So I think that's maybe the idea that I'm going to be good enough with, and that feels linear time, because at worst, if the number is the first number, if k is 0 or 1, I don't know if it's 1 based or not, Does it tell you that it's one? Okay, it's one based. Okay, they should be more explicit, but that's fine. In that case, you just go up rows number of times, or maybe the other worst case is if it's on the other corner, then you go up rows number of times and then columns number of times, right? So R times or R plus C, sorry. So I think that's going to be good enough for me to try to think about it. I'm generally historically very bad about these problems because they are really just really one-off and brain teasers, right? So your experience may not really save you, but having kind of, you know, having the experience, having an idea and a good way to kind of search your, almost like a meta kind of way, search your type of algorithms will give you maybe something to play around with, at least for the easier ones. So that's basically what I'm going to do now. So let's say rows is equal to the length of the matrix, and we're just making sure that they are at least one element. And then columns is equal to length of matrix of 0. And then here we start by, let's just say xy is equal to, let's see, columns will have 0 because we want it to be on the first column, and then on the rows we have rows minus 1. And of course, like I said, you can also start at the other corner. I think the same logic mostly apply, and even if it didn't, you could just flip it and then do the same logic. But I think there's some symmetry there so that you could have that answer. So here now, let's see. I think the harder part about starting from this corner is that now we have to try to do the math here in an inverted kind of way, but that's okay. Because I think what I'm doing is actually finding the kth largest number, but you can obviously see the symmetry between the largest and the smallest because it's just R times C minus that number, right? So maybe we'll do that instead. You goes rows times columns minus k. Maybe it's off by 1 because I think this is 1 indexed, but we can play around with that. But let's just see if we can get us closer. So then here now we go while target is greater than 0, or maybe greater than equal to. Like I said, right now we're still just playing with the ideas. We'll play around with the exact off by 1 or whatever later, just to kind of get an idea. I think actually if I was more confident about programming, I would probably the implementation, I would probably just really define these things accurately. But I like things having 0 index because usually that makes more sense. So yeah, so then now when target, because when you have 0 index, when target is equal to 0, then that is your answer. Okay, so now while target is equal to 0, we look at we look to the right, and to the right there are columns minus y minus 1 candidates, right? Because basically if you're in columns 0 on the 0 index, that means that there's columns minus 1 to the right. If you're on the 1 in the 0 indexed first column, then you have columns minus 2 and so forth, right? So let's just say the right is equal to numbers, so to the right is equal to this, and then now we check to see. I think there's some logic that I may be missing a little bit. I feel like I'm missing a little bit as well, because I think I do make an assumption a little bit on that, you know, because here if we eliminate these to the right, what do we do about this duplicate number? Or even just, you know, this doesn't have to be duplicate even. It could be, say, a 14. And what does that mean? And I think I'm not being super clear about it. Let me think about precisely what does that mean, right? So to the right, these numbers, let's also just say up is equal to rows minus 1. Or x minus 1 actually, sorry. Right, so that's the numbers that we consider. And then the question is, can it be in this row? Because I don't know, it's a little bit weird because let's say the answer, oh no, okay, I guess that makes sense. No, okay, because I was going to say, what if you eliminate the 13, then you 14, but we only eliminate this if we know for sure that the number is not in here, right? So I think that's okay. So if target is greater than right, maybe equal to, this is very awkward. Let's see. Let me think about this for a second, hang on. So if this is bigger than right, then we move up because it can, and not, well, actually we should also consider the current number. So if this is, okay, let's see. So only if this is strictly greater than right, we can eliminate it. Is that true? Well, okay, let me go the other way. If the right is greater than target, then if the numbers is greater than or equal to target, meaning that, for example, if target is 0 and right has more than 0 numbers, then we should go to the right. So then now here we go y increment by 1. We continue. Yeah, because we don't eliminate any numbers. Well, I mean, we kind of eliminate the numbers to the upwards, but they're all smaller numbers, and we're trying to find the biggest number. I like I said, I maybe messed up some stuff here, or I probably made some stuff confusing instead of choosing this corner, but we're here now, so that's what we're gonna do. Okay, and then else, is it always good to eliminate? Yeah, because if it's not in there, then we can eliminate. Is that true? Because basically what I'm saying in code is that if it is not to the right, if the number's in the right, we go to the right. But if it is not in there, can we always go up? I don't know if that's true. I think that's kind of the issue with these, I wouldn't say it's greedy in this case, but these greedy E problems is that you have to prove this correct. And for me, that's what I'm trying to think about right now, is just counter examples and whether I can prove this correct. So for example, if we're looking for 4 numbers and we eliminate 3 from here, but then we may think that this is the last number, which is here, but that doesn't really make sense, right? Let's play around with this for a little bit, and then we'll see. And then here, if we go up, then we know that we eliminated right -1 actually, because we should eliminate this current cell as well. Here, yeah, but this feels very wrong, to be honest. So yeah, I don't know. Let's play around with this. Let's, you know, now that we're close to the thing, we can also, you know, just run some cases and see what it's wrong. And with some good luck, actually it is wrong on the test cases. And I say good luck because you better, especially on a contest or whatever, you better have the wrong answer on an obvious thing than you know, or something that you know the answer to versus some random number. But we can also just be a little bit exhaustive in just doing like 1, 2, 3, and see kind of we can notice a pattern of sorts. I mean, we know what the expected answer is, but what our actual pattern that we get from here, right? So I think that's mostly it. There's a 9 to kind of see how is it wrong, right? Somehow maybe it's going an infinite loop if it's taking this long, which means that something is very wrong. Oh, yeah, that means, I mean, clearly it's wrong now, but it means that this goes by. Oh, in this case, we remove one number because when we go to the right, we eliminate the current cell. So maybe that's a little bit better. Okay, so that is the reason, though it does not give us the right answer. Okay, so at least it converges. So for 1, it gives us 9 because it goes bam bam, and then you have 3. If this is inside here, what does that mean? I think I counted backwards. Yeah, because for this one, I think I counted backwards. Even though we eliminate 1, for example, we're looking for 0. If k is 1, I guess in this case, if k is 1, which means that it's 0, index 0, then we search for 9, which means that we minus 3, and then we go to the 9 instead of the 1. And I'm not sure. I mean, I'm obviously my thing is wrong as well, and this is actually. I mean, I know that we have the expected answer here, but this can also be very easily verified, which is why I do it this way, at least for this particular problem, because you just have to sort it in your mind or something. But do I even get the same column right? I don't even get the column right? Because for 6, how did I get 15 for 3? I meant rows correctly. So ideally, you even get the rows correctly, and for k is equal to 3. Oh, maybe I did this the wrong way. I think I meant maybe this is right because k is 1 indexed actually. Yeah, I think I had an extra off by 1 here, though apparently it's giving me an issue. Like I said, these ones are really hard for me. Which one is it getting wrong on? Okay, so k is 1, then we search for 8 in this eighth largest number, which makes sense, and then is it just 1 directly? Okay, so it's all of them. So if this is 8, we subtract. Oh, whoops. I meant right plus 1. Well, whoa. Okay. That's a big mistake, actually. Okay, so now we seem to do a little bit better, but it's still wrong, because of this case where I think I don't handle this correctly at all. I mean, that was one of my reservations, and also I got the ordering backwards on the top row, but that's okay. That one is actually easier to fix, but unfortunately, right now it's just looking at it row by row, which is like essentially what I'm doing is just division and modding, so this isn't quite right, even though it looks complicated. Also, that if k is 1, meaning this is we want to try to find the biggest number, then we actually even get it wrong because we just look at here and then we just stop short. So maybe I'm thinking from the wrong corner. Let's see if I'm thinking from 15, what happens, right? Well, if we go up, we still eliminate all these. And the tricky thing is that if this is 13, it doesn't really matter either way. But All right, let's play around this. If we, let's say we're going here, and we want, do we go up? No, but the way that I constructed is a little bit weird. I think there needs to be a better decision rather than just these two. Because like I said, it's going to be just like a variation of modding and dividing, which is clearly not the right answer. Okay, so I think from that, there's one more invariant that I need to figure out, right? Something that is held true, but I don't know how to do it quite yet. I mean, you can also do a binary search on the thing, but that just feels a little bit icky. Is there a linear time one? I feel like there's a linear time one, but okay. So let's say we're at the 12th. And we, how do we decide to go up or right? I mean, I did this thing, but it's clearly wrong. We go to the right if is there another way to do a frontier type thing? I mean, like, maybe this just doesn't work going up, down, left, right. Oops, how did that happen? And here, if I go up, I eliminate all these numbers, but that's not good enough for, because if we have a 14, we eliminate the 14 by going up, even though, yeah, so that the answer could still be here. So maybe we have to think of another way of doing it. Okay, let's say we have 15. Can we eliminate, I guess the question for a linear time solution is, can we eliminate a row and a column at a time? And I don't know, maybe you cannot. Because if we go up, that means that we eliminate all these numbers, but we know that this number is awkward. How do we eliminate the entire row or column by itself? Well, at the bottom right corner, we know that this is the biggest number. So then the next biggest number is either here or here, right? And then the next biggest number after that is either here, here, or here. But then it just becomes like a heap sort type thing, right? So I don't think that's, or I mean, it could be the answer. It's just not a linear answer, right? Like if we go 15, we go 14, and then we come back to 13. It's already, but then you expand to 9 and 11, but that's not good enough. Man, this is a brain teaser, and I've been really bad about these. That's why I don't think starting from 15 makes sense, but does it make sense to start at the 12th? Still thinking too much about binary search answers, but that will not get us to a linear solution. So, because 12, you can binary search in the last column now, but that's a little bit awkward as well to figure out how to eliminate stuff. Yeah, I don't know. Yeah, I think I maybe alright. Well, I'm just going to do it with the heap way, I suppose, and then we'll figure out if there's a linear. We'll learn if there's a linear solution. I can figure it out, but I also cannot prove the lower bound. So that's the other thing that I might do, or one who is very good or better at math would do to count the lower bound is kind of reduce this to a sorting problem or something like that, or a sorting network, compare-based sorting network. But yeah, I don't know. But yeah, okay. Let's do that, and then we'll see where what logic I'm missing, and let's play around with that. Okay, so let's start at. Can I do a heap in a smart way from that then? 12. If I eliminate the, I don't know. Okay, let's just do the learning thing. I'm always spending half an hour on this, so okay. Okay, so let's start a heap. And this is a min heap. So in Python, so let's start at the corner, the smaller corner, and then we'll just go up. And then while target, length of heap is greater than 0 if target is equal to 0, return current is equal to we go straight up. Current xy is equal to heap q dot heap pop of h. Okay. And then we just, yeah, I guess we also just keep track of whether we've been there. Okay. For dx dy, and let's just say go down and go to the right. And that's pretty much it. Okay, maybe not. Apparently. Dun, dun, dun. How does that happen? Oh, whoops. Yep. Yeah, looks good. Let's give it a submit. And this is going to be r times c log r times c, which is a little bit sad. I mean, it's going to be good, which we knew it was going to be good, but still. All right, let's see if there are any. I mean, definitely, I feel like there are better solutions. So let's kind of do some learning here. Let me also just start another window for it, another tab. What is going on? New interface is kind of cool looking, but it makes it really hard to search. Like, it takes too long to load. I don't need it to load all my history before typing in the search. It's just actually suboptimal, but well, let's first of all see if I've done it in the past. It's possible that I have, but let's see. Nope. Okay, so the solution is pay to win. So let's kind of see party queue. It's not okay, but that's not what. Binary search, heap, find and sort. Okay, so maybe I just spent a long time trying to figure out a linear time solution, which is kind of sad now that I wasted a lot of time about it, but okay. So let's go over this. So I mean, obviously there's some heap solution, there's some binary search solution, and there's just a regular sorting solution. And the idea here is just, you know, you pop up one item at a time, and for each item the next number that we get is going to be the smallest, and in a way that will give us the answer. Here for each element we push each for example, if k is the largest element, you're going to push this element, push every element log r times c time, so the total time is going to be O of rc times log of rc. And in terms of space, it is just O of rc, or r times c if you want to be more precise. Yeah, I think that's all I have for this one. Yeah, it's awkward because I was really hoping for a linear solution one, but yeah, let me know what you think. Even though I knew how to do it this way, it would have took me like really quickly. Yeah, let me know what you think. Were you full? Did you try to get a linear time solution? Let me know. And when I say linear, I mean r times c, because that's linear in the size of the input. Yeah, that's all I have for this one. Stay good, stay cool, have a good rest of the week, and I will see you later. Bye bye.